the current induced has a field that's in the opposite direction of the field that created it. So since the field was increasing into the page, remember, the field is into the page and we're increasing it. Since the field is increasing into the page, then the induced field must be out of the page. So for the induced field to be out of the page, we're going to use the right-hand rule, and you're going to point your fingers in the direction of the current. And let's say that the direction of the current was, let's say, counterclockwise, then your thumb points out of the page. If the current was clockwise, point your fingers in the direction clockwise, and your thumb points into the page. We want the magnetic field, or your thumb direction, to be opposing that which created it. So it should be out of the page, and so the current in this case must be must be counterclockwise. So that's what the minus sign actually is telling us, is that the current induced is counterclockwise, where the magnetic field was increasing in, and so the current is that way, so that it creates a field which is out, right? So the induced field is out of the page. Okay, that's Lenz's law and Faraday's law. So here's another example. Let's take, we did this kind of thing before, but before we had run a current through, I believe we had run a current through this apparatus. But let's say that we've got this apparatus where we've got a U-shaped metal, conducting metal, and a bar, right? So we've got the U-shaped thing, this right here. And then we've got a bar, this cylindrical bar that I have moving at speed v. It's not actually moving at speed v yet. Let's just put that bar down and make electrical contact so that there is a closed loop. Let's put the whole thing in a magnetic field, constant magnetic field B. Doesn't change, constant magnetic field B. And the field is everywhere. So again, I didn't draw it everywhere. But the field is everywhere. Okay, field is everywhere, and it's constant. And let's just give this thing dimensions. When we put down the bar, it's a distance W from the other end, and the whole thing has a width or a height of H. And we want to induce some current in this apparatus, and we can induce current by moving the bar. If we move the bar, we're increasing the magnetic field through the loop, right? Through this loop, we're going to increase the magnetic field through that loop because we're going to make the loop bigger. So we're going to increase the flux by moving the bar. So how much? We should give the whole thing a resistance. If the whole thing has a resistance of, or we can just talk about the induced EMF, I guess. What is the induced EMF? Therefore, we could figure out the induced current if we knew the resistance. If we pull the bar at a speed v. So when it's sitting still, there should be no induced current because nothing's changing. But when we move the bar at a speed v, what is the induced EMF? So we're going to use Faraday's law, right? So Faraday's law says the induced EMF. And again, the direction doesn't really matter. The direction, if we want to know the current, the direction matters. But for the induced EMF, or let's just ask, what is the magnitude of the induced EMF? Magnitude. So the induced EMF is minus n d phi dt, but we'll just get rid of the minus sign. So the magnitude. Okay. So in this case, the flux n ddt, the flux is B, right? B doesn't change. And A, the area, is W times H. But W is changing, right? So it is equal to, right? Because as we pull on it with V, W changes. So we've got N. And so what changes? Oh, sorry, I didn't say. I didn't even write down the integral, right? Because everything's constant. Everything's constant. At an instant in time, right? The flux is integral of B dot dA. In this case, is just equal to B times A at any instant in time. the flux here is equal to B times A. And I just skipped the whole argument of the dot product and the integral. So B times A is B times W times H. So now we have to ask, how does that change, right? How does that change with time? Well, B doesn't change with time, so B comes out. H doesn't change with time, so H comes out. But W changes with time, so we've got dW dt. And what is dW dt? How much does W change with time? That's just the velocity V, right? Or the speed V. So it's NBH times V. So the induced EMF, the magnitude of the induced EMF is just NBHV. Oh, and what's N? Whoops. Take back that box because N was given, right? What was implied? What is N? N, it's a single loop circuit, right? It's just one loop. So in this case, N is just one. So the induced EMF, the magnitude of the induced EMF is, in terms of the given variables, is just BH times V. Okay. So I could give you values, right? I could say that this is a tabletop thing. H is 10 centimeters. I pull it at a meter per second, and B is, 1 Tesla. And so, you get a induced EMF of 0.1 volts, something like that. So that's, and then if the resistance was 1 ohm, then you get a current of 0.1 amps. So anyway, that's the induced EMF. Okay. That's another example in the books. Oh, we should talk about the direction. I didn't ask for it, but what's the direction? So the flux is increasing into the page, right? Because the flux is pointing into the page and it's getting bigger, and so the magnetic field that's created must point out of the page, and the magnetic field that is, in order to create a magnetic field out of the page, then it must be counterclockwise current. So the current is going to be counterclockwise in this loop. Okay, just trying to come up with other examples. It's there's not a whole lot more we can do until we get unless we were to get a lot more complicated. But let's just take a coil, 10 loop coil with total resistance of 0.1 ohms, and copper wire coil. Let's say we start with a magnetic field of 0.1 teslas at 45 degrees to the plane of the coil. And we turn down the field at a constant rate in a total of 30 seconds. So we go from 0.1 teslas to 0 teslas in 30 seconds. What's the magnitude of the induced current? Well, so first of all, the magnitude of the induced current is only going to be induced while the field is changing. So we're only going to induce current for those 30 seconds. Right? So the EMF, the induced EMF, the magnitude of the induced EMF is equal to IR, which is equal to N d phi dt. So the magnitude of the current, we'll just write it as a magnitude without the absolute values, is N over R d phi dt. Okay, so again, it's going to be N over R times the time rate of change of the flux. The integral of B dot dA. Hopefully by now you can tell how to do these integrals and dot products. Now, while B doesn't change over the area, it is at an angle. So therefore, B is still constant over the area, but let's just write it out. But the angle, the dot product, right, BDA cosine theta, there's a 45-degree angle. So we've got ddT of the integral of B dA times the cosine of theta, where theta is 45 degrees. That's 45 degrees between B and A. That's been given. But now B is constant over the area, right? You got to be careful. It's not constant in time, but it's constant over the area. So B comes out of the integral because the integral is over the area. Got to get used to that. So it comes out of the integral. Cosine theta is a constant. That's constant over time and area. So that comes out of the integral and out of the derivative. So what we end up getting is N over R ddt. I'll just write it this way. ddt of B cosine theta times dA, which is just N over R ddt of be a cosine theta, right? So we already said that on the other page, that as long as things don't change over the area, if they only change in time, then the integral just turns into the constant flux formula, be a cosine theta. And then what changes with time? What changes with time in this case is b. A and cosine theta do not change with time. So this turns into n over r a cosine theta dB dt. Because the only things that change with time is the magnetic field in this case. So we can go to the next page. And so therefore I is equal to n over r a cosine theta dB dt. And now all of those values are given. N was 10 loops. Area was... oh, I didn't give you the area of a loop. Darn it. Meant to give you the area. Let's just say that the area is 1 square centimeter, which is 10 to the minus 6 square meters. Sorry, I didn't give you much room there. Area is 10 to the minus 6 square meters. So N over R, which was 0.1 ohms, and area 10 to the minus 6 square meters, and theta cosine 45 degrees, and dB dt. What is dB dt? Well, B goes from 0.1 Tesla to 0 Teslas in 30 seconds. So it's So it's 0.1 Tesla per 30 seconds. That's just in magnitude. If we included the sign, it would be B final minus B initial over total time. So it would be minus, but we're not including the signs. We're just looking for the magnitude. So this is the magnitude of the current. It's the magnitude of the current induced. You can go ahead and plug that into your calculator if you want, but all I really care about is getting the right formula. We can plug it in and figure out what the current induced is.